Welcome back. Today we're going to talk about scientific notation with positive powers of 10. Okay, scientific notation, so I'm just reading off the top here. Let's go through it. Scientific notation is a notation that is used to express very large or very small numbers. Okay, and we use scientific notation so that it's easier to understand the number size. Today we're only going to talk about the large numbers. Tomorrow we're going to talk about the small numbers, okay? We can rewrite the number as a number between 1 and 10 times a power of 10. Or, so in parentheses, it's a number between 1 and 10, so that's going to be our first factor. We're going to rewrite the number as the product of two things, so you have two factors. So a number between 1 and 10 times a power of 10. Now this is just a picture of the solar system, and I wrote this here because it's called scientific notation because this is the notation that scientists use. All right, when you have distances, very long distances, for instance, like the distance between Saturn and the Sun, or the distance between Mars and the Sun, what you want to do is instead of writing them with all the digits expressed, you want to use a compact form of the same number to express them so that it's easier to understand how much bigger a number is from another number. So it's a way to compare numbers. Okay, so let's deal with, for instance, the weight of a blue whale. A blue whale weighs 250,000 pounds, and this diagram just shows you, you know, if this is the size of an elephant, then a blue whale is this size compared to the size of an elephant. It's this size compared to the size of a human. So it's 97 feet in length typically, whereas an elephant is only 9 feet in length. So it's 10 times bigger almost than an elephant. So if the weight of a blue whale is 250 pounds, well, what we're going to do is we're going to take 250, and it's important to understand that when we write a number in scientific notation, we're not changing the value of the number. We're just using a different notation to express the same value. Okay, so I take 250, and one thing I could do is, well, 250 is 25 10,000s, right? It's 25 times 10,000. That's one way of thinking about 250,000. Another way of thinking about it is it's 2.5 100,000s. So it's 2.5 times 100,000, right? So this number, 2.5, is actually where we're going to settle on because this number is between 1 and 10. Okay, and we're going to rewrite 100,000 as 10 to the 5th power. Now, we can see that it's 10 to the 5th power. It's easy to see powers of 10 because we can just count the number of zeros. 1, 2, 3, 4, 5. So it's 10 to the 5th power. Okay, another way of remembering this is if you think about 10 to the 1st power, that's just 10, right? 10 squared, that's 100. So you can see that the pattern is that the exponent matches the number of zeros. One exponent of 1 gets you 1 0, and so on. So 10 to the 3rd power would be 1,000, right? It's 10 times 10 times 10. And again, you see the pattern continues, that the number of the exponent matches the number of zeros. So that's, in fact, how it goes. So 10 to the 5th power is going to have 5 zeros. So we're using this notation to make it more compact. Now, it doesn't seem more compact between 250,000 and 2.5 times 10 to the 5th power. But if you had a number with, let's say, 30 zeros in it, then it's much more compact to write it in scientific notation than it is to write it in what we're going to call standard form. Okay, this right here is called standard form. So standard form is just the number expressed the way we would in every other class except science class and math class for the moment. But scientific notation is expressing it as the product of two things, a number between 1 and 10 and a power of 10. So let's get to our definition here. Scientific notation is, a number is in scientific notation if it is written in the form a times 10 to the power 10 to a certain power, okay? And so the restrictions on A. Now, A has to be, I said between 1 and 10, but to be more specific, it can be equal to 1, right? This is the greater than or equal to symbol. Or equal to. So it can be greater than or equal to 1, but it has to be strictly less than 10. Okay? So 10 itself, written in scientific notation, 10 would be, it's interesting to note that 10 would be written as 1 times 10 to the first power. Okay? That's because this number right here has to be between 1 and 10. It can't, or it has to be greater than or equal to 1, but less than 10. Okay? So be careful of that number. Be careful of this. This is called the coefficient right here. Okay. Now b, this b can be an integer. We just learned about integers. Integers are the whole numbers, right? And their opposites. Dot, dot, dot. So the next lesson is going to be what happens when b is a negative power of 10. So when the power of 10 is negative, when b is negative. This lesson we're just going over when b is positive. Okay? Now, b is also called, the power of 10 is also called the order of magnitude. So if I say, for the last problem, I say, what is the order of magnitude of the weight of a blue whale? You'll say 5, because it's that exponent there. So make sure you have this in your notes. Okay? So what you're going to be asked to do is take a number that's either written in standard form or this is written out. It's not written in mathematical notation. It's just written verbally. But you're going to have to be able to go from standard to scientific notation and back the other way. Okay. So if the distance from the Earth to the Sun is 93 million miles, then standard form would be 93 with 6 zeros, right? Because we go all, this is the hundreds places and then the thousands places, and then you have the 93 in the 10 million spot, okay? The 9 ending the 10 million spot. This is 93 million, so that's standard form. Now, if you're going from standard form to scientific notation, what you're going to do is divide by powers of 10. Or you can think of it as rewriting it as, so it would be 93 times a million. Right, it's 93 millions, except, so this would be right here, it would be 93 times 10 to the 6th power. Except remember this number is not in scientific notation because our coefficient here has to be between 1 and 10. So instead of writing it as 93 millions, let's write it as 9.3 10 millions. So it's 9.3 times 10 million. I'm using equal to signs because they're all equal to each other, but this number finally is going to be in scientific notation. So it's going to be 9.3 times 10 to the 7th power. Okay, so here I could have seen this here by, if the decimal place was here, I want to get one more power of 10. If I divide it by another power of 10, I'd have to add 1 to the exponent here. So this right here, I'd go 9.3 times 10 to the 7th, which is exactly what I got if I rewrote it as 9.3 times 10 million. Okay, so here, this number is in scientific notation because you have a coefficient between 1 and 10, and you have something in the power of 10. Okay. If I were to take a number that's in scientific notation and I had to, the instructions here should be rewrite it in standard notation. Okay, because it was already in scientific notation. So here, if I want to rewrite it in standard, well, this is 3.5 and this is 10 to the 6th power is a million. Okay, so 3.5 1 millions is 3 and 500,000. Now that might not be, that might not be very easy for you to do. I mean, I've been doing this for a while, so it's easier for me to see that. But another way to do it is to think about moving, when you multiply a number by a power of 10, so 3.5 times 10, for instance, what you could do with the decimal place is move it to the right one. This would be 35. Well, 3.5 times 10 squared, what you're going to do is move the decimal place twice. So 1, and it gets, when you move it once, it gets to the end of the number, so I have to move it again and add a 0. So this would be 3.5 times 10 squared would be 350. Notice that's the same as 3.5 times 100, right? 3.5 hundreds is going to be 350. So another way of thinking about going from scientific notation to standard notation is to take the number and move it the amount of, so if you think of this as the amount of places you have to move it, then you want to move the decimal place 6 spaces to the right to make the number larger. So you have 3.5. If you move it 6 spaces, well, moving it 1 space gets you to 35, and then that's moving it 1 space. You have to move it 5 more spaces. So 1, 2, 3, 4, 5. You end up adding 5 zeros here. So this ends up being 300. So 35 with 1, 2, 3, 4, 5 zeros. We can go back in and fill in the commas here. Okay, so that's one way of looking at it. One thing to note, however, is that this was the number we started with, that the exponent here does not always match the number of zeros. So these two things do not necessarily have to match. So they do not have to match. It's really important to note here, because what ends up happening is a student will get a number in scientific notation, like let's say 2.67 times 10 to the 9th power, and they'll think, oh, that's the shortcut they'll take is 267 with 9 zeros. And that is not the case, because what you do is you have to move it 9 spaces to the right. So we go, this is 2 spaces to the right already, so we're actually only adding 7 zeros. Okay, so after I add the 7 zeros, I can go in and add the commas wherever they need to be. But it's very important to understand, I lost 2 of my moves here. I lost 2 of the zeros, if you think about it, by moving to the right twice, and then I could add the zeros in. So that's a common mistake, right? So this lesson you learned about scientific notation, and you learned how to move back and forth between standard notation to scientific notation. And that's the end of the lesson for today.